Hello, everyone, and welcome to our seventh chapter on climate. This chapter is a very important one, and we are going to be covering a lot of ground in it because climate is such an important concept in environmental sciences. Our list of learning outcomes for this chapter is pretty extensive. We are going to define both climate and weather and explain how the two are related. We familiarize ourselves with the Celsius temperature scale as we do this. We will discuss the role and mechanisms of the major controls of Earth's climate, which include insolation, albedo, and the greenhouse effect. We'll also identify and describe the mechanisms of major internal and external changes to the climate, which will include solar output variation, volcanoes, biological processes, changes in glacial coverage, and meteorite impacts. We'll look at the processes that can lead to a climate state that is known as a snowball Earth and contrast the factors that influence this period in the Earth's history with other factors, such as the ones operating during the Cretaceous period. We'll look at the major ways that carbon dioxide is added to and also removed from the atmosphere and describe how carbon dioxide and greenhouse gases can be kept in balance. We'll describe the changing climate of the Quaternary, which is the current period of the geological timescale that humans are in right now. And in doing so, we will look at how processes called the Milankovitch cycles explain the variations seen in climate over the Quaternary period. We'll explain how the glacier and climate systems are linked through albedo effects. We'll describe how sediment and ice cores provide information about past climates. We'll look at how stable isotope fractionation is used to predict the impact of changing climate. And we'll assess long term global temperature records and place recent climate change into the context of historical temperature observations. And we're almost done, I promise. We'll explain how changes in the sun's energy output have impacted the past 1300 years of global temperature records. We'll look at the ways that humans have influenced the Earth's albedo, as well as explain the initial and long term effects of volcanic activity and why they are different. We'll explain the enhanced greenhouse effect, discuss how recent observations of changes within regional ecosystems are related to global climate change, and explain the relationship between fossil fuel usage and CO2 emissions. Before we get into real meaningful discussions of climate, we need to clarify two foundational ideas, one of which is the distinction between Celsius and Fahrenheit. You probably know that both of these are scales for measuring temperature, which is an important aspect of climate. If you were born and raised in the US, the one that is intuitive to you is probably Fahrenheit. If you were born and raised almost anywhere else, the one that is intuitive to you is Celsius. The US is one of only 5 countries that use Fahrenheit as the official temperature scale. The others are very small countries like Belize and the Bahamas, and they're so small that they can barely see them on this map. But because Celsius is the much more common scale for measuring temperature in the context of the world, it is also the scale that is used in science. So we have to familiarize ourselves with the Celsius temperature scale a bit before we get started. So let's take a look at some of the temperatures that you might be familiar with in the Fahrenheit scale and compare them to the Celsius scale. In Fahrenheit, water freezes at 32 degrees, which is the same as 0 degrees in Celsius. A comfortable room temperature in Fahrenheit might be around 68 degrees, which is the equivalent of 20 degrees in the Celsius scale. In Fahrenheit, the human body is 98.6 degrees, and in Celsius, it's 37 degrees. A hot summer day in Arizona might reach 110 degrees Fahrenheit, which is 43.3 degrees Celsius. Then, water boils at 212 degrees Fahrenheit, which is 100 degrees Celsius. So, one of the convenient things about Celsius is that freezing and boiling are sort of anchored at 0 and 100, respectively. Those are easy to remember. Also, Another thing to note is that when water goes from freezing to boiling on the Fahrenheit scale, it goes from 32 degrees up to 212 degrees, which is a difference of 180 degrees. When water goes from freezing to boiling on the Celsius scale, though, it jumps from 0 to 100 degrees, which is, of course, a difference of 100 degrees. So, to cover the same amount of ground from freezing to boiling, Fahrenheit does it in 180 degrees, while Celsius does it in only 100 degrees Celsius. Actually, this tells you that the interval of each degree in Celsius and Fahrenheit is not the same. 1 degree Celsius measures a bigger change in temperature than 1 degree Fahrenheit. In fact, 1 degree Celsius is almost twice as large as a degree Fahrenheit. So keep that in mind. When we are talking about temperature changes in Celsius, those are bigger changes than would be reflected in our understanding of Fahrenheit. And of course, there is a standard equation that is used to convert between Fahrenheit and Celsius and vice versa. To get from Fahrenheit to Celsius, you take the number of degrees in Fahrenheit and subtract 32, and then you multiply that number by 5 ninths. If you need to go from Celsius to Fahrenheit, it is the reverse. Take the number of degrees in Celsius, multiply by 9/5, and then you add 32. So that's one foundational idea that we need to clarify. The other is the distinction between weather and climate. Weather and climate are two terms that are often mistakenly used interchangeably, but they are not the same thing. Weather describes the short term state of the atmosphere in a specific location and time, including the conditions of the wind, air pressure, and precipitation, cloud cover, humidity, and temperature. Climate, on the other hand, describes the average long term atmospheric conditions, including the yearly and seasonal weather patterns. So, weather is the word to use if you're describing localized and temporary events, while climate is the word that describes the big picture of trends and conditions on Earth. One example of a statement that correctly uses the term weather would be the weather yesterday was 41 degrees Celsius, whereas a correct way to use climate in context would be during the last ice age, the average global temperature was about 8 degrees Celsius. So now that we understand the distinction between weather and climate, we can dive into the major factors that influence the Earth's climate. These include insolation, albedo, and the greenhouse effect. We're going to walk through these one by one, starting with insolation. Insolation is the term that we use to describe the amount of solar radiation falling on a surface. Higher insolation means that there is more sun exposure. Lower insolation means less sun exposure. A very salient example of where we can see the effect of insolation in action is the difference in temperature between the Earth and Mars. If you take the average temperature of all parts of the Earth, it's 15 degrees Celsius, which is about the yearly average temperature in San Francisco. On Mars, the average temperature is 60 degrees lower at negative 55 degrees Celsius. A major reason why this is the case is because of the level of insolation that each planet receives. Earth is 95 million miles from the Sun, whereas Mars is 155 million miles from the Sun. So, with its closer proximity to the Sun, the Earth receives higher levels of insolation than Mars does. And this higher level of solar energy coming to the Earth system is reflected in its higher temperature. But insolation doesn't just affect differences in temperature between planets. It also affects temperatures within the Earth system. because different parts of the Earth receive different amounts of exposure to sunlight. Namely, the poles, meaning the North Pole and the South Pole, receive less sunlight than the equator does. This is because the sunlight at the equator strikes the surface of the Earth at a more direct up and down angle, whereas at the poles the sun strikes at a more of a slant. You can see this in the illustration on the left. What the illustration on the right is showing is the fact that sun is more concentrated when it hits a surface straight up and down. You can see that this beam of light that is straight up and down covers a certain distance, but when we take a beam of light with the same diameter and tilt it at a 30-degree angle, the surface area that the light covers is bigger and more dispersed and less concentrated. So the amount of energy hitting the surface from the angled light isn't as powerful. The difference in the insolation at the poles versus the equator explains the very different temperatures that occur in these regions. This illustration shows the average annual temperature in different latitudes of the globe, and you can see that the poles are obviously much colder than regions closer to the equator, and this is a consequence of different levels of insolation. Insulation also explains why the planet has seasons, and why the seasons in the northern hemisphere are the opposite as the seasons in the southern hemisphere. When it's winter up here, it's summer down there, and vice versa. The reason why this is because the Earth is making its yearly orbit around the Sun. It is also simultaneously spinning on its axis, which triggers our night and day cycles. But this axis is not perfectly straight up and down relative to the Sun. It's tilted at a 23-degree angle, which causes different levels of insolation to occur in different parts of the globe over the course of the year. So here we see a representation of the Earth during the month of November, headed then to the Northern Hemisphere winter. And you can see that because of the axis tilt, the Southern Hemisphere is actually more exposed to the sun during this time. The South is leaning toward the sun, while the North is leaning away from the sun. This, of course, makes it so that the Southern Hemisphere is getting higher levels of insolation and the Northern Hemisphere is getting lower levels. Down here on the surface of the Earth, this manifests in it being a hot season versus a cold season. But then, as the Earth continues along its path orbiting the Sun, the direction of the slant changes. At some point, both the northern and the southern hemispheres are getting more or less the same amount of sun exposure, and this is the point where it is spring in one hemisphere and fall in the other. And then the tilt of the axis causes the slant to reverse. The northern hemisphere is the one that is leaning towards the sun, and the southern hemisphere is leaning away. And as a result, the northern hemisphere gets more insolation and the southern gets less. And this manifests in it being summer in the northern hemisphere and winter in the southern. So, bottom line, the tilt of the Earth's axis leads to variations in insolation levels over the year. And that's what gives us our seasons. These images here show differences in the level of solar insolation across the globe. This offers a comparison between what it looks like in January versus April. And you can see that in January, the highest insolation levels are in the southern hemisphere. And then by April, they are climbing higher and higher north. And finally, insolation doesn't just change over the course of the year, it has also changed over the course of Earth's geologic history in many different ways. The solar radiation that the Earth receives has increased by about 10% for every billion years of its history, and the Earth is about 4.5 billion years old. Also, the shape of Earth's orbit around the sun also changes over long periods of time. We're talking tens of thousands and hundreds of thousands of years. And its axis tilts tilt, and direction of axis rotation also changes. It hasn't always been a 23-degree angle that the axis is tilted at. That's just what it is right now. In addition, the sun has a solar cycle where solar radiation levels peak every 11 years and then ebb. But the impact of the solar cycle is relatively quite small. The peak levels of radiation that happen every 11 years are only about 0.1% higher than the lowest levels of radiation. Nonetheless, that's another factor that dictates changes in insulation of the Earth over time.